Okay, so one of my favourite topics within A-level maths is around log modelling or log graphs. And I think logs are really cool. In the world of data science, actually, there are specific applications for logs, and one of them is actually sort of built upon what you learn in A-level maths. So let's just take a really basic scenario here. We've got some observed data, which we can plot as a scatter graph. Okay. Now this is a very nice sort of scatter plot, but you know, we might believe that there is an equation that could link x and y together. Okay, and you know, we might believe that actually it could be an exponential equation, it could be a polynomial equation. So an exponential equation means something of this form here. So we could believe that there is a relationship between these two variables in that form where a and b are to be determined, or we could believe that they are in a polynomial form. Okay. Now, how does logs help us to find these constants? Let me just look at the polynomial form here. So if I believe that my data can be related or modelled in this equation, then I can use logs. But how? Well, if I believe that y is equal to this, then if you remember your laws of logs, there's one little law that isn't really talked about that often. It's not even really a law, it's just a little fact that you need to know. If the log of two things are equal, then this is basically derives that those two things must also be equals. It actually goes both ways. So if something equals something else, then the log of that must equal to log of this. So what we can do is apply that logic here. If these two things are equal, then log of y must equal log of this. And then, hold on, we've got a product within this log, so we can use addition law. And we've got a power within a log, so we can use power law. Now I'm just going to rewrite this for convenience. So what does this do? So logs are really cool, that's the title, but why? Because what we've actually got here, if this data has a relationship like that, what we can actually do is apply logs in such a way that we can actually get a straight line or get close to a straight line graph. But how? Well, a logarithm is really interesting. It's a type of function that can actually linearize your data. So anything that's multiplied or set to a power, it can actually, by using logarithms, you can make it into an addition between those sort of same constants, a and n and whatnot. But instead what we're going to get here is a scenario like this. So what we've got here, on the y-axis we've got log y, on the x-axis we're going to have log x, on the n, what is n? n must be our gradient, and log a is our constant. So what we can now do is transform this graph to log y against log x. So if we had our data set as a table, x against y, we can transform that to log x against log y, and then we can plot those points. Now, if those points, what you'll notice when you plot those points is that they should be fairly linear in nature. And if you were to draw a line best fit between them, that would essentially be what this is. Okay, so the y-intercept of this line is c, which is log a. The gradient of this line is going to be n. Yeah, and those are the two constants you want. So this n value, this power, comes from finding the gradient of that line from that log graph, and this a, this other constant we need to find, comes from basically setting log a equal to c and then transforming that to get the value of a. So that's why logs are cool. They can essentially take real data and transform it into a scenario where you can find constants if you believe that there is a relationship between the data, whether it's polynomial or whether it's exponential. There you go.